Okay, can we make a start? I have to say, if there was a nice, gentle hush like that every lecture I gave, I'd be delighted. So down to the speaker already. So welcome to this inaugural lecture from Professor Alex Tapper. The series, for those that aren't aware, gives us a chance to celebrate our new professors, or indeed, in Alex's case, those that were minted during COVID. So it's been a while, but it's really great to have this opportunity. As the title suggests, Alex is a particle physicist, so as the head of the particle physics community here at Imperial, it gives me the opportunity and the pleasure to host today's events. So let me do that. Let me just start with a couple of kind of housekeeping rules. We are not expecting a fire alarm, so if the fire alarm does sound, please use the emergency exits to move out to the assembly point, which is on the corner of Exhibition Road and Imperial College Road, in that direction. As you've probably seen, the event is being recorded. There will be an opportunity for both those in the room and those online to ask questions, so please hold fire till the end and we have that opportunity. Very few brief words of introduction to the topic and to the speaker himself. Particle physics, all about the fundamental, the basic building blocks of nature and the forces that govern them. So on the one hand, elucidating the origins of the universe. For me, there's always this fantastic contradiction, dare we say that, with the fact that typically the equipment, the collaborations that we use to answer those fundamental questions, large, multinational, they barely fit in this room, let alone this building. And Alex has been really pivotal in those two areas, both the underlying physics and indeed the development of the techniques. And I know we'll hear about some of that today. So very modest, but to have really led those two activities is absolutely fantastic. And in particular, on the physics side, searching for physics beyond the standard model, so going beyond our best understanding of the current picture of the standard model to look for new physics. And on the detector side, the instrumentation side, on the trigger, or as we'll hear, the real-time selection of the events of interest, the sheer data volumes that we collect, far too large, or have in the collisions, far too large to actually record, need to process that in microseconds. That's the technique and area that he's particularly focused on the instrumentation side. Those techniques, as we'll hear, can be used in particle physics and beyond. So an absolute fantastic remit of activities that we're going to hear about. Alex completed his PhD with the Zeus experiment in Hamburg. So great acronyms. I get in at least the first, but you'll see many as we go through. Spent some time as a postdoc on that experiment, then moving across to CMS at the LHC, first as a research position, and then as a member of staff here in the department, and then progressing through very nicely, very quickly to professor, as we've said. Just to give a couple of highlights from CMS. Alex is too modest to stress them. You'll see the content, but let me just point them out. He led the largest physics group, as examples, he led the largest physics group looking for physics, or new physics beyond the standard model within CMS. That led to some of, if not the most highly cited papers in that area from the LHC. And on the trigger side, he led the overall level 1 trigger project. So level 1 is the first step in this selection of events of interest. Get that wrong, it's all wrong. You never get it back. So the single most important step as we go forward. So as we'll hear, maybe he gave the spoiler so I can say it. No new physics was seen. The Higgs was found. I was looking in that area, but without his trigger boards, I couldn't have found the Higgs. So we'll hear about that as we go forward. But absolutely fantastic range of activities. Looking to the future and the upgrade of the LHC, Alex is the PI on the CMS UK upgrade project. That's a project that I have also the pleasure of working on. So it's with great pleasure I can say over to you, boss. Alex, please. Thank you.
So thank you very much for coming. It's some considerably better attendance than I usually get for my lectures. And I'm aware that it's sunny outside, so it can only be the promise of wine afterwards, I'm sure. So when people ask me about my research, I usually just tell them, well, I'm searching for new stuff. And sometimes that's enough, but sometimes they then say, well, what do you mean? And it could surprise me, it could be anything. And then some people are satisfied with that, but some are not. And then they ask things like, well, why would you do that? And how would you do that? And did you ever find anything? And even, why should I pay for you to do that? So these are all, of course, completely reasonable questions. And I'm going to try and answer them this evening. Possibly not the last one. So you can mentally prepare yourselves. There'll be lots of pictures, almost no equations, and almost no chance that I finish within the 40 minutes of allocated time. Okay? So we begin with why. So before we can answer the question why, we have to understand, what's wrong with the model that we've got. Why do we need a new one? Why do we have to find something new? And so we're going to start with a history lesson in 4 or 5 slides, explaining the current status of our knowledge of particle physics and the universe. And then I'm going to point out some of the perceived problems with that. And then we're going to discuss how we might move forward and solve those problems. So let's start with matter. So Democritus apparently was the first person to use the word atoms, and he said the first principles of the universe are atoms and empty space, which on the face of it is a statement that holds up pretty well today still. This is apparently what Democritus looked like. Wikipedia is a little bit sketchy on whether that's really him, but he could have looked like that. So let's suppose that's him. The other thing to note is that he lived a remarkably long time, for 500 years BC, so that's a good long life. So then smoothly moving over 2 millennia, we'll get to 1900. So just before 1900, J.J. Thomson discovered the electron. It's, of course, a pivotal moment. And then people started to ask what atoms were made of and how this electron fitted in with the overall idea of atoms. And so Thomson proposed this plum pudding model of the atom. So basically, the pudding is the sort of orangey color there. That's positively charged. And then the plums are the electrons, the negatively charged stuff stuck inside them. And so that was, that's a proposal. That's something we can test. And then Rutherford devised an experiment to find out whether that was right or not. And he got Geiger and Marsden to do that experiment. So what he did was they fired alpha particles, like these lines, through a very thin foil, which is basically like atoms. And if Thomson were right, then most of the alpha particles would fly straight through and hardly be moved at all, right? Because this is not very dense. What really happened was that most of them flew straight through like that, but 1 or 2 came bouncing back through a really tight angle like that. And that told Rutherford that rather than have this overall pudding, there was a really, really hard, dense center in the atom here, a positive center. And he went on then to try and quantify this. Next in line was Niels Bohr, so this was only, I think, 10 or so years later. And he came up with the Bohr model of the atom, which is very much the way I thought about this when I was an undergraduate, right? So the nucleus, I don't think he knew about protons and neutrons at that time, but that's what's there. The nucleus is in the center, that's the hard bit, and he said that the electrons, they orbit around the nucleus like a small solar system, right? And that's like a useful picture to have in your head. The really, really special thing that he said was there are only certain orbits they can follow, right? And that means that if an electron changes from one orbit to another, there's a very fixed characteristic amount of energy it gives out, and that was in agreement with what people had observed and couldn't be explained by this. So this was already a very, very sophisticated and useful picture of the atom, and one that I still find useful to think about. These days, a more modern picture is to imagine that the electrons are like a cloud around the nucleus. And you can see as you move out in radius, the cloud gets into sort of funny shapes. And indeed, some of these are rotating. And so, the orbit model is not so crazy, right? And so this is the way we think about it these days. And somewhere in the cloud, when it interacts, you find the electron. We can actually image this from a paper in 2013. They have sort of 10 images like this of different hydrogen atoms and in different states. So you can really see these days that that's what's inside, right? So that's more or less electrons, right? Now let's look inside the nucleus. I said it was protons and neutrons, and that was known for a good long time. And then in the 1950s, an experiment was done in Stanford in California, and if you can just about see here that these dots here, they don't quite sit on either of the 2 lines there. And that was the first evidence that protons are not elemental, that there's not fundamental particles, that there's something inside them, right? And that something is quarks. We now call them quarks. And based on these results, they built a very long collider across the San Andreas Fault in Stanford, and they did more than a decade of amazing experiments to characterize what's inside the proton. The short answer is that you have some quarks, an up and a down, and a proton is 2 ups and a down, and a neutron is the opposite. There's a bit more going on there than that, but that's the headline, if you like. So now we understand what's inside the nucleus. That's your protons and your neutrons made out of your quarks. Outside is electrons. And then there's one other particle that makes up normal matter, if you like, and that's a neutrino, and we're going to discuss that in a slide or two. So, moving along. Now we move to the forces. So once we have the matter has to interact. Different matter particles interact with each other, and they do so through forces. So I've chosen to start with electromagnetism, and we'll see why later. So magnetism was well known. I think it was known by the ancient Egyptians and is recorded there. They found rocks that were, either attracted or repelled each other and used these. They also knew about electricity. They knew that there were certain fish that when you touched, you got a shock from. So these things were known a long time ago. And then really there was a lot of work, particularly on electricity in the 17th century. The key moment probably is Maxwell. This is 1876 or something, I think. He realized that electricity and magnetism were really the same thing, right? So when a current moves, like an electrical current, that makes a magnetic field, and vice versa. And so he showed that these two things that we thought were different, completely different forces, were actually manifestations of the same thing. And of course, he wrote down a bunch of his equations here, and now you can see these on novelty t-shirts in physics departments the world over. Yeah, I think that's all I wanted to say there. So that's the reason I cover that first is it's a nice example of unifying two forces and realizing that they're more or less the same thing. Of course, there are three other forces. Gravity is the one that we're probably, on a day-to-day basis, most aware of, right? But there's a problem with gravity, which is that gravity, as described by general relativity, so Einstein's theory, it doesn't play well with quantum mechanics. They don't get on. You can't fit them together. That's not news. People have known that for 100 years, and it's a glaring problem that people have been trying to work on, but extremely difficult. As a particle physicist, given that we work with extremely small particles, gravity doesn't play a role, and we don't talk about it, and that will be the rest of the lecture. I've got nothing else to say on gravity. Okay? So, two more forces, the strong nuclear and weak nuclear forces. The strong is probably the most intuitive one, right? So we said that inside protons and neutrons are quarks. Well, something has to hold those quarks together, right? So that you get protons and neutrons. And that's the force inside there that holds them together. And it's hard to know who to credit for this, but Gell-Mann and Zweig had the idea of the quarks and probably a good deal of the interaction as well. The weak nuclear force is a bit more difficult. It's not something in our day-to-day lives directly. So beta decay, radioactive decay, what happens is that a neutron turns into a proton and an electron, and that happens at some rate. If you look at the energies of the proton and the electron, then something's missing, and this is this neutrino, which I mentioned before. So this was postulated by Pauli, who thought he'd done something terrible by saying, I'm going to create a particle that you can never find. And a lot of the theory was done by Fermi. So this is radioactive decay, but it's also the force that allows the sun to burn slowly. Otherwise, the sun would have already burnt out and we'd be all cold and dead. The fact that this is much, much weaker than, for example, the strong force means that the interactions in the sun go at a slower rate, and that's why we're still alive. So those are the forces. So where are we? We've got the matter, we've got the quarks, the up and the down, the electron, we've got the neutrino here. These forces are carried by particles. That's the way we understand it in quantum mechanics. So when two particles interact, they exchange a force-carrying particle, and that's how the force works. So the way we usually describe this by analogy is that I'm ice skating with you, I've got a ball, and I throw the ball to you. As I throw the ball to you, I'm going to go backwards, right? Everybody can see that. And when you catch the ball, you're going to go the opposite direction. And so the ball is the particle we're exchanging, which is the force, right? And that's a repulsive force, because we're going to end up further away from each other, right? And so that's basically the idea. We can stretch it a little bit further and say that if it's a tennis ball, maybe we don't move so far. And if it's one of those big medicine balls that you see in training, then we're going to go further apart, right? So far, so good. It's more difficult to describe the attractive force. If we're ice skating and I throw a boomerang and you catch the boomerang, then maybe we end up together, right? But I can't ice skate or throw a boomerang, so it's not going to work at all. So the ball that we're exchanging is these things here. So the gluon is the ball when it comes to the strong force. The photon is the ball when it comes to the electromagnetic force. And then this Z and W, these are the balls somehow together for the weak force. It's a bit more complicated than that. The Higgs boson is on here too. It's not really technically one of these. It does get exchanged. It's not really a force, but it has other properties that are in common with these, so we list it there. So we're almost done. We've almost got all the particles. There's one little surprise to go, which is that there's 3 copies of all of this. So like we had the up and the down quark and the electron and the neutrino, then there's another one, and then another set as well. And they're exactly the same, just heavier. And we don't know why that is. Right? There are only 3. We've done an experiment. The answers were 3, not 4, not anymore. But we don't know why that is. But yeah, at the end of it, that's all the particles and all the forces, excluding gravity, in the universe. And you can write down all the interactions between these and how everything works. And a very simplified version is there on a mug that you can buy at CERN. We call this the standard model, which I think just proves that if we started off in ancient Greek and we worked through Latin and German and English, we haven't really come up with any creative names. It's not the only standard model. There's a standard solar model and a bunch of other standard models in physics. So we're not as imaginative as we might like, I guess. So what's wrong with this picture, right? I mean, this all sounds quite good so far. I sort of hinted that we don't know why there are 3. That's something we'd probably like to know better, right? So that's something that if we had a new theory, we might like it to tell us why there are 3. But there are some other problems too. I'm just going to pick a few examples that... So a nice, potentially easy example is dark matter, okay? So if we have a galaxy down here, the galaxy is spinning around like this, right? And the particles in the center of the galaxy, they're not moving. And as you go further away from the galaxy, they're moving, and they increase, so they get faster and faster until some point where they're outside the galaxy, and then they fall off like this. And this is a calculation that many of us in the room could do, right? This is Newtonian mechanics, A-level calculus. Not impossible. So that's great, except when you measure it, it doesn't do that at all, right? It shoots up like this and it keeps on going, maybe flattens off a little bit, right? And this was, of course, a surprise, or in the end a surprise. It took quite a long time to get there. And so the way we interpret this is that it kind of follows this curve up to here and then it diverges, and there's got to be something here. There's got to be some matter that we can't see with a telescope there, right? Some matter that doesn't appear to be in the stars here. And so this is the evidence for dark matter, the gap between these two. And the fact that it follows it here means that this is kind of like a halo around the center of the galaxy. So we even know a bit about how it's distributed there, okay? If we look at what we know about matter, it turns out, okay, dark energy we're not going to cover here, but dark matter is like 23% of the energy in the universe, and the stuff that we know is very, very small. So this probably isn't the most embarrassing problem in physics, but it's really quite an embarrassing one. Right, because we only understand a tiny sliver out of this part here. So if we had a new theory, for example, if we discover a new theory, we'd like it to solve this problem for us, wouldn't we? So there are a couple more. So remember that I said that we like to unify the forces, right? So like it turned out that electricity and magnetism turned out to be the same force in the end, just a different manifestation. Well, in general, we'd like that to be true. We'd like all the forces that we know about to basically come at the very highest energy to be the same thing, and then we see that they're just different manifestations at the energies that we can measure. That would be very attractive, wouldn't it? So it turns out that the weak force and the electroweak force, which I think are the green and the blue in this diagram, they do that. If you look how strong they are, then at some huge energy they kind of meet, right? And that was proven, that was proven by Abdus Salam, whose Nobel Prize you can see on the wall when you leave for doing exactly this. But if you then put on top of that the strong nuclear force, you see that this red line doesn't meet those two. So that's another thing that we kind of like. If we had a new theory, we'd like it to fix that, right? So that the 3 points came together and we'd understand things a bit better. Good. My final example is unfortunately technical, but it's quite important to the work that I want to show you. So I'm going to try and explain it to you anyway. So particles, when they're moving along, they can fluctuate into pairs of other particles and then recombine to be the original one, right? Or they can be traveling along and they can spit out another particle which they then absorb later. This is just something that happens at the quantum scale as particles are moving around. They're allowed to do this because this happens very quickly for a very small amount of time, right? So this is just the nature of particles. And that's completely fine. For most particles, if we do this with a photon, then it would go to 2 particles and recombine. It makes calculations a bit of a pain, and we should probably understand it a little bit better, but basically it's not a problem. However, it is a problem with the Higgs, because the Higgs boson couples to the heaviest particles it can find, and therefore when the Higgs is traveling along, it's looking to find the heaviest particle it can in this diagram here and the heaviest particle it can here. So that's fine, except that the heaviest particles up here we would expect to be extremely heavy. I mean, if it's a gravity or something, then it's like 10 to the 19 at the Planck scale. I'm going to explain what that is in a minute. And the Higgs is like 100 or something. So it's 10 times 10 times 10, 17 times is what we would expect the mass of the Higgs to be. But it's not. And so something funny is happening there. Something is cancelling that out, right? And it's just a colossal coincidence, which we don't like. And so we'd be much happier if a new theory could find a way to explain that huge coincidence. And this is actually the one that originally was driving the work that we were doing, trying to understand this. Okay? So, is there a solution to all of this? Well, I'm going to give you an example. So supersymmetry is an example theory beyond what we call the standard model. It's just an example. There are other ones, but this is the most studied and probably the best understood one. So what this does is it says for every particle that we know over here in the standard model, there's another mirror particle, right? They differ by the spin that they have. And spin is a quantum mechanical number, so I won't try and explain it too well, but it has the same mathematics as rotation, which is why it's called that, right? But for each particle that we know, there should be another particle, and it should be exactly the same except for this funny parameter, right? And so why would that be useful? We're just doubling the number of particles we've got. That's not helping us understand things much better. Well, it turns out that one of these particles, probably the lightest one, of these new particles could be dark matter, right? We don't have a candidate for dark matter. All the particles that we know don't fit. They can't be the dark matter. But we could have another set of particles that could be the dark matter. So that would be great. That would solve problem number one. Problem number two, the complicated one, the hierarchy problem. Well, now, for every particle we've got going around in this loop, we've got another particle that it's its partner, and it turns out that comes with a minus sign, right? So every time we add some huge number in this one, we subtract it in the other one. So in some very elegant way, we've solved our huge coincidence, right? And finally, there's an extremely technical one here in a paper that I find it very difficult to understand from Coleman and Mandula. Basically, this says this is the only symmetry you can apply and not break all the interactions that we have. And so that's a kind of argument like, if it can happen, then probably it happens. So that's, for some people, a reason. So this seems like a great idea, right? I mean, we pay the price of twice as many particles, but we could solve all our problems. The other problem it solves is the unification one, right? So this one, the red line missed, and this one, the red line hits it. So we're happy about that, too. So that's all great. Where do I find it, is the next question, right? So there's a couple of ways that you could figure out where to look. And this is where it gets a bit more complicated, okay? So this is from 2008. So if you take all the data in the world in 2008, and you say everything that I know about cosmology and particle physics and all these other measurements, and you say, and if I put in this supersymmetric idea as well, where's the best fit, right? Where does this model most likely to lie? Then the answer is this black dot here, right? And then, the uncertainties are these colored bands here. So these axes are masses. We'll come back to those, but it's the mass of the dark matter candidate. So basically, this tells you a point. It tells you that's where you need to look, right? And, it might not be there, but it kind of should be here-ish. So that's number one. This is driven by data, right? Number two is driven by this hierarchy problem, right? And so, the new particles can't have exactly the same masses as the old ones, otherwise we would have found them, right? So they must be a little bit different. That's okay, but then if they get too different, it doesn't solve the problem. It doesn't cancel this stuff out. So the question then is, how different am I willing to accept? And that's a little bit subjective. So this is from Nima Akani Hamid. He's chief theorist in our business, probably, in 2011. And this is what he thinks. He basically says you have to find these three particles in these mass ranges, right? And the first one is the Higgs, and the other two we're going to come back to. But the numbers here are like 1,500 and 400. Those are things to remember, right? So when we're searching for the dot over here, and we're trying to find these particles at least below where he said there. So look, it was 2010-ish. It was extremely exciting. We knew exactly where to look. And so we went off to try and find these things, right? And that leads us to how. So now we know where to look. How do we do it? So the dark matter stuff, dark matter we look for with telescopes. Particle physicists don't know one end of the telescope from the other, right? So we've got to find another way to do this. And there are at least three nice ways of doing it. So one way is that you can have a big tank of liquid in a mine, which is what this one is here, and you have your standard model particles you know about are in black, and the dark matter is in blue, and they sit underground in a mine deep off somewhere, and what you're waiting for is one of them to come in and just scatter and bounce off one of the standard model particles. So that's one way of doing it. We do this experiment here at Imperial, based in the US. You can then kind of rotate that, and you can say, what if my two dark matter particles came together, collided, they produced some energy, and the energy then produces some extra particles. So that's another way of finding it. This is the AMS satellite, so this is a detector in space that does that. And finally, you can rotate the diagram once more, right? And you can smash together two particles that you know and hope that two dark matter particles appear. And that, of course, is the most fun one. So that's the one we'll do. Good. So it happens that we have a collider just when we needed it. So the Large Hadron Collider at CERN, I guess, is reasonably well known. So this is in Geneva. There's the Jura Mountain on one side and the Alps on the other. There's a 27-kilometer circumference tunnel and 100 meters underground, and a bunch of experiments. And what happens is that protons, two beams of protons, go round and round these things. They go at almost the speed of light, which is very difficult to imagine. So it's probably easier if I tell you that the 27 kilometers, each proton goes around that ring 11,000 times a second. So maybe that makes you think a bit more than that. And then they smash together, and you need a detector around where they smash together to figure out what happened, right? They smash together 40 million times a second. We'll need that number later. Good. So here are some photos from around 2006, 2007, when we were building the experiment. So here's me on the phone, trying not to look like a tourist for the photographer. We built the experiment above ground, and then it was lowered, all 12,000 tons, 100 meters underground, really carefully, and put back together. Here's Matt, who's here, looking through the center of the detector. And it was a great time, a lot of fun, very exciting, and lots of hard work. Here's Rob, peering through. This is the center of the detector, all made of silicon. And this thing here that looks like a kebab is being lowered down, and it has that inside it, and then slides in there, right? And that's the kind of almost the last piece. And then you're finished, finally. So it's closed, right? That's how we all close this together. And if you want to know what's inside, there's silicon first and then some other things. There's a whole sort of onion inside there to capture the particles, right? So good, we've got the detector. Remember that I said that these protons, they collide 40 million times a second, right? And the detector has 100 million channels. So it's like a 100 megapixel digital camera, which sounded much more impressive in 2006 than it does now, but still. But the impressive thing is it takes 40 million photographs a second, right? So that's really a lot of data. Now, I could tell you how much data it is. It's thousands of exabytes, but it's probably easy to show you. So the size of the circle here is the amount of data. And we could take Netflix. So this is 140 million hours a day of streaming Netflix, and that's that size. This is all the email sent in the world for a year, and that's sort of that size. We could pick out some other things about Google Cloud and Amazon. And then this is our data, and you can imagine this circle goes all the way around here, right? So when I say big data, I really do mean big data, right? So that's a problem, because we've got to do something with this data, and we can't store it. There's too much of it. So how do we address this problem? Well, first of all, we think about what's inside there. So this here tells you what happens when you've smashed two protons together. This is a cross-section, which is basically like a probability, right? So the really probable stuff lives at the top, and the really unlikely stuff lives at the bottom, right? And we're on the red line here, okay? And you can see this spans from like, what's 10 to the 9? That's a billion, right? Down to 0.001 or something. So a huge range of here. So most of the time, what happens at the top is the two protons hit each other. Maybe they just bounce off. Maybe they break up a little bit, but it's not really very interesting. I wouldn't be getting out of bed for that, really. As you move down here, you get to slightly more important things. And this sort of level here, I would say, is calibration. So for me, interesting stuff starts like 1 in a million or 1 in a billion. And then the really interesting stuff is right down here, right? So, what's that? There's 100 billion, 1 in 100 billion or something is down here. So that's the stuff I want to get at. And then all the boring stuff that, to be fair, other people do make measurements from, and it's not boring for everybody, but all the boring stuff is at this point here. So I need to find my way to get these, bearing in mind that I can't just take everything. And so that's a bit of a challenge. Fortunately, it's a challenge that was solved a long time ago. So Patrick Blackett, Lord Blackett, whose building you're in, for his Nobel Prize, he says, I set about, therefore, the devising of a method of making cosmic rays take their own photographs. So, back in the 20s and the 30s, we didn't have particle colliders. So if you wanted to do particle physics, you relied on particles falling from the sky, right? So cosmic rays. So what you do is you set up your detector and you'd wait, and if you were lucky, then something fell through it. And you have to take a photograph at the same time. So basically, you sit there taking photographs, and if you're lucky, you might get something happening, right? Which wasn't a very efficient way of doing it. And what Blackett did was to make a way of finding the really, really interesting stuff without having to go through millions and millions of photographs, which is the analogy to what I was doing. So if I get this right, so particles come from the top. The numbered things are detectors, and this absorbs some stuff. So what happens is he says, I'm going to take a photograph if number 1, number 2, number 3 say yes, and number 4 says no. So that means that a particular momentum of particle has come through here, lost some energy, and stopped in this part here. And using this, they were able to take this photograph here, which is hard to interpret, but I believe is a muon, so this second copy of the electron. And this had been discovered at the time, but this was kind of strong confirmation. So great, so we have, he got the Nobel Prize, which is also outside on the wall, which you can see on the way out. So great, so now we've got an idea. We've got this huge amount of data. We want to get 1 in, what did I say, 100 billion out of this. And we can use a technique a little bit like this, but we'll probably try and use a computer or something a bit faster. So again, I could tell you that we have to process this huge amount of data in a small amount of time, and I could give you some numbers, but it's probably easier to show you. So on the left-hand side, this is the data rate. Again, the size of the circles is the amount of data, and this is the time you have to do it in seconds, okay? So you can see that Netflix is kind of here, and Google Cloud is kind of here, and the big blue thing is us. So you basically get a millionth of a second, 10 to the minus 6, to process this big blue thing here. And so it turns out that computers can't do that. Computers work on the millisecond level, so they're like 1,000 times too slow to do this. So we built our own. Right? And this is the thing here. So this is, we built a whole set of these systems. I've got one here. You can come and touch what part of the LHC later if you like. Underneath here is a custom chip. And you plug in a whole load of optics at the front here, and you make a system like this that works all the data. And that's the thing that Gavin said, helped him discover the Higgs and helped us search for this. So that was our technology part, if you like. So now we're set to go, I think. Right? We've built the detector. We've got everything that we need. And so we can move on to what did we find. Good. So what did we learn? So now we have to look at some results. So it was a very exciting time, and we took data first in like 2010 or something like this, and we wrote this paper here, which I don't expect you to read. But what do these things look like? So this is the end-on vision. So right, the proton comes in and out of the board like this, right? And remember, we're searching for dark matter particles that we can't really detect, right? Because they disappear from our detector. So what you see in the detector in the center is you see some other particles, and then you see a big gap over here, right? If you wanted to balance this, you'd want to have like another 2 particles. And these are the ones that are missing, right? So that's the sort of thing we're searching for. The variable we do it with is here. You don't need to really understand this, except that any dots over here are good. And this part is not so good. So you can see there are 2 or 3 little dots here. Unfortunately, that's exactly the amount that we expect from background. So there was no dark matter here. And then we need to learn how to read these, right? So these are masses in the theory. This is the mass of the dark matter candidate. This is the mass of some other particle in the theory. And when we don't see something, we draw a line on here, right? And we say that if it falls underneath this line, then it can't be, because we would have found it. Right? So we rule that part out, we exclude that. So if you have a theory that predicts something over here, then I can say, no, that's not true, right? And then above the line, to the top right, that's something that's too heavy, I can't make it, I can't tell you anything about it, right? So that's what we do when we don't find something. We draw a line on this graph that tells us what's allowed and what's not allowed, right? And remember, we were supposed to be searching for this little point down here. It's like 300 and something, so it's probably just above there with a ring. So our first go, we didn't really get there, right? But we proved that it all worked and got together. So good, we weren't disheartened. It was the first paper on this. We were a little bit worried that we might have screwed up and looked like idiots, but it turns out we were right. So then we tried to look again, 30 times more data the year after, more or less. And you can see there are a few more points up here, but sadly, unfortunately, the same number what we kind of expect. And then we draw the same sort of line again, and remember we're looking at 300, which is kind of here, and about 50. So this time we got beyond that. So we were able to say, well, this looks a bit dodgy, right? These particles are not what we expected them to be. But, you know, there's still some of this big red band that's poking out. So it's not completely a done deal that these don't exist. Okay. So then we moved on again, and we tried to do it with 20 times more data again and a little bit more energy. This is a slightly different graph, but you know, this is, remember the famous theorist? He said this should be like below 1,500, so just off the graph here. So we went too far away the first time we tried, and he didn't really say much about this particle here, but it should be okay. So we were still getting there, but we didn't quite find it. And then, once more, we had a lot more energy, but a smaller data sample. And this is also a little bit different. So this, again, is the 1,500. We're kind of almost there. And this is the one that he said should be 400. So that should be right in the middle there. So I would claim that his prediction there is in trouble, right? I mean, there are caveats here in the sense we don't cover every single corner, but subsequent analyses did cover most of this. So we probed more or less up to where it was supposed to be, and we didn't find anything at all, which you'd think would be a bit of a CV killer. But it turns out that thousands of people cited our paper, so thousands of people were interested that we hadn't found anything. So that was quite nice. And so that's pretty much the story of this search. The story is that we basically haven't found what we were hoping to find or what was predicted to be there, but it turns out that not finding something is also kind of interesting. And now what are we doing? Well, we wondered, you know, if we can't find these particles, might they be somewhere else? Might we be looking in the wrong place? And so one thing that comes to mind is, what if these particles don't get produced when the two protons hit each other at this particular point? What if they're produced there, but then they have a long lifetime, and they fly a little bit in the detector, and then they appear somewhere else? I mean, we didn't build the detector to do that, so it doesn't do that very well. So it's kind of hacking the detector. So we started to look at that, which we'd realized in one of the last papers. And so you can see there are lots of different possible signatures here, but basically, you know, everything flies out from this central point, and then something happens. And so we most recently, these are the sorts of events that we've been looking for. For the connoisseur, there's a Feynman diagram here, and the thing we're actually searching for here is a heavy version of the neutrino. But sadly, we haven't found anything there either. But this is looking in, if you like, in another dimension. And this is bringing us right up to date. This is a paper we published this year, which is rather nice. So what happens in the future? Well, it turns out I can carry on doing this for another 15 years, which is nice, isn't it? So we're somewhere in this blue thing here. We've got another 2 years to run, and then we're going to close down for a few years and make the detector better or make the accelerator better, and then we're going to run for another decade. So I could easily see out my career like this, or more or less. So what we're going to do is we're going to build a better detector. The better detector will have better electronics. So this is the new version of the board that's down there. One of these boards can handle the broadband internet of a small town, and we usually put 12 of them together. While everybody else is making wonderful, quiet, efficient laptops, I mean, my MacBook doesn't even have a fan. If you have some of these running, you need to put ear protection on, and you don't go in the same room. So we're building hotter, louder computers. If you could think of a reason to use that, then we'd be very happy to sell you one. It's very niche. The other thing we'll be doing a lot more of is machine learning. So Shani estimated at a workshop I was recently at that it will be 25 billion inferences a second. So basically, here we're going to have more intense collisions, so we're going to have more and more of these tracks and more particles colliding. It's going to be a really big mess, and the only way to pick out all of that stuff is probably with machine learning and artificial intelligence. And so those are the two things that we're working on together in the world of this upgrade, which the UK and the other countries are taking part in. And we should get 10 times more data, possibly slightly higher energy after this running. So now I'm going to tell you why I think it was worth it, which is not quite the same question as why should I pay for it, but it's related. Okay? So the science first. So it seems to me, at least, that supersymmetry doesn't seem to be the solution to this hierarchy problem. It could still be the solution to dark matter, and that would be fine. Supersymmetry is such a beautiful idea that it may well exist at a higher scale. It's just it doesn't solve the problems that we want, and it's not, you know, something that I could observe. There's no evidence yet for dark matter particles. The search goes on. For me, that's really probably the most motivating thing. We know that something that we don't understand is happening there in a large part of the universe, so we ought to address that. And you know, the spin on not finding anything is that this challenges us to think of new ideas, I think, and that's a healthy thing. On the technology side, these trigger systems are challenging technology, but vital to our science program. We're expanding to do more real-time processing and more of this AI, on a chip, and even quantum computing to do this. And I'll be surprised if there are applications beyond what we do for this. So I find that very exciting. So that's why it's worth it from the science and the technology point of view. I think the real reason why it's worth it is the students. So here are all my students. This is the sort of work burns through a few students. And most of them have now graduated, which is good. And they are really the product of this, or the thing that I'm probably most proud of. So they leave, some of them stay, most of them leave to go into data science or government or some other thing. And they're highly numerate, deep thinkers, which is what we need. So thank you to them, certainly, and I think this is really the product. So the moral of the story. There are 3 morals of the story. The first moral of the story is that you can't boss nature around. Even the smartest humans that we've got, even if they agree on something, if it's not there, it's not there, right? The second moral of the story, I think, is that a negative result can be very positive. It makes people think in new and different ways, and we're still waiting for the outcome of that thinking, but it's good. I think the other thing that we learned probably is that we had to develop this processing, this data processing, which is very niche. It's something that we work with industry on, but is not, the tools that industry use are not really adapted for us. And I think that's a very positive thing, the interaction with industry, the driving things forward. I think in the world of going forward with AI, that's going to be a big thing. And finally, again, possibly the most important thing, very little science is done by one person at a time here, and I did this with a huge number of people. I can't possibly imagine having done this on my own. I think that would be impossible. And I've enormously enjoyed working with thousands of people from all over the world with all sorts of different cultures. And it's mostly, with a few exceptions, been an absolute joy. So I would recommend it, and I get to use my GCSE German and French on a daily basis, which I never imagined I would do. So really, to finish, I have to thank some people. There are so many people to thank that I'm just going to thank some people from Imperial and upset everybody else. So Rob and Oliver are the people I work most closely with on the analysis. Since Oliver's not here, I can say that the thing I learned most from Oliver is that he has an exquisite sense of how well you have to do something for it to be acceptable, and does not go one step beyond that. So I think we learned a lot of pragmatism. On the technology side, Kostas and Greg couldn't make it, but Andy is here. We're the people who work together on these, again, with a sort of rotating cast of other people in both cases. But these guys have been the key guys. Andy and Rob are yin and yang. Sorry, Andy and Greg are yin and yang. Greg can dream up a million ways that the project could fail or something could go wrong, and then Andy will talk him out of it. So it works perfectly. And finally, at the bottom, so I should thank Louis Lyons for getting me into this business as an undergrad. And then Ken Long, my PhD supervisor, sort of taught me how to do most of this. Jeff Hall taught me how to get stuff done in enormous collaborations when people disagree. And when things went wrong, Jeff was very helpful. Paul Dauncey is an inspiration to me. He's an inspiration because he does fewer things than me, but really, really well. And I aspire to do that. But I find it so difficult because there's so many interesting opportunities. But lately, I've been thinking of Paul when there are opportunities and occasionally saying no. So I'm going to keep him there for that. And finally, Gavin, who introduced everything, who's head of our community. Gavin has all the answers, always. That's the simple thing. Well, they're usually right, whether it's about physics or how to treat people or how to solve a problem. Gavin always knows the answer, so huge thanks to him. And of course, to all the other people and all the other people all over the world, and in particular, to these two. And I'll finish there.
Absolutely fantastic, and if I may say, I turn to the clock. Alex's modesty, bang on time. No overrun.
More luck than judgment.
Questions from the room and also remote. Let's start with the room. Any questions from the room? Go ahead. Actually, could you just wait for the mic? Sorry.
Yeah, so thank you for your talk. So you've developed these new chips to process data so quickly. What actually makes the data processing really quick on these chips?
The chips are FPGAs, so they run at a slower speed than the CPU in your in your laptop or a GPU, but they're enormously parallel. So if you can wrangle your problem into something that's very parallel and they're incredibly customizable, then you can get a real speed up with those. So it depends exactly on what the problem is, but this problem is very amenable to that.
Question in the room on the, just under the
So I'm just going to have to run down.
Sorry.
How can you be sure that you haven't missed anything in the data if you're not keeping it? That there may be something that you weren't programming in your algorithm and it's just actually the thing you should have found.
Yeah, so that's a great question. Traditionally the way we do that is we have what are called pass-throughs. So instead of applying this decision-making to the data, for some smallish amount of the data, we just let it go. So we take everything. So that's the control sample, if you like, to make sure that your selection is right, and also you might find something unexpected in the control sample. Now, it's not foolproof, because you're not, there could be something very rare hiding in there that you wouldn't take enough data. More recently, we're using machine learning to do this. So you can do this with variational autoencoders, which we won't go into too much, but basically, this learns what normal data looks like, and compresses it. And when you decompress it, if it doesn't look like normal data, then you can tell. And so this is something we've just started trialing. We're just running that this year in a sort of parasitic way. So, but that, in principle, is one technique to make sure that you haven't missed something just because you didn't think of it. But it's something that, for sure, we worry about. Yep.
Question to the back.
Do you ever think about how gravity might fit into the standard model?
I'm not smart enough to think about that. No, I mean, I don't even understand the problem well enough at a sensible level. I mean, quantum mechanics is bitty, right? And quantum field theory is basically, think of as tiling the universe with little oscillators, and then general relativity is all smooth, and they just don't fit together. And that's all I can tell you.
Any other questions? No, maybe we pause and see if there's anything online. Go ahead, Rob.
Okay, no questions at the minute, but there are one or two comments that basically talk about how clear and elucidated the points were. So that's always good, given that this is a live stream. Maybe I could ask a question in the meantime. I mean, you talked about high luminosity LHC, and that will keep you busy for the next 15 years. I mean, you showed one diagram which showed the very busy events. I mean, how will the trigger system evolve in the future?
So I think that machine learning is going to end up being the key to this, and that's pretty scary because it's a black box, and we have to as the previous question or the questioner before said, how do you know that you're throwing away the right stuff? And at the moment, we're selecting events in a way that I can understand, and in the future, we'll be selecting events that in a way that I don't understand as well. And it's even more critical. But I imagine that's the only way that we'll be able to process the amount of data in an efficient way. So we better get good at it. That's pretty much my thought.
I think we've got two more questions. One here, I think was maybe the first hand I saw, and then one in the middle. Yeah.
Induce machine learning into this, how are you going to train your models? Like based on what would the models be trained?
So if you're using machine learning to parameterize some reconstruction, like, all those green lines, right? They come from a point, so you want to find the vertex where they all come from. So that's a straightforward thing. We can train that with offline samples of data that we've taken, and that's fine. But yeah, there's a whole category of ways that you would use this where you don't want to bias yourself, and so you would use unsupervised learning for that, of the type that I talked about with the autoencoder, for example. But there are other ways of doing that sort of thing. But it's very challenging, certainly.
There was a question there, but maybe just as we hand over, I could add, we use machine learning already very extensively. So what Alex is really focusing on for the next steps is then this step to using it in the trigger where we bring in the data, as he says. But the average analysis at LHC may have 10, 20 BDTs, neural nets, some kind of machine learning in them already. So it's progressive. Yeah. Sorry, question in the middle.
How do you source the energy for these supercomputers?
So that's a very good question as well. So most of the energy at CERN, I think, comes from nuclear power in France, because the accelerator itself is takes a lot of energy, and so does computing. CERN is working on net zero and working on a way to, is on the path to making that more environmentally friendly. It's actually very difficult science to make environmentally friendly. We have a white paper out recently on how we could transform our field in the future, and it's very, very challenging. So it's for sure a problem and for sure something we're aware of, but a work in progress.
Okay, any other questions in the room? Yeah, so one over that side.
I could add actually that our boards here are more energy efficient than GPUs by quite a long way. So if we could find a way to do more AI with them, that would be net good, probably.
I'm a bit of a fanboy for Sabine Hossenfelder. I expect you probably know her. I think she's a respectable physicist who became a YouTuber. And her opinion seems to be that the amount of money, the amount of resources that are currently spent on, well, the LHC and what will not come after the LHC aren't really justified by the amount of research outputs that have happened in the last few years. Because there's no guarantee that you're going to be the necessary energy levels. How would you answer that?
So the LHC was no lose, right? Because you either find the Higgs boson or you don't. And if you don't find it, that's exciting. As I've tried to show you that my not finding stuff's exciting. For not finding the Higgs would be even more exciting. So that was no lose. But that's an unusual situation to be in. I think in previous generations of colliders, we haven't had that guarantee. And it's been exploration. And so I think, in some sense, the exploration, not having a guaranteed outcome, is the normal state of affairs. And the LHC, marketed very well by our forebearers, has put us in a position now where people kind of expect that. Having said that, experiments are getting more expensive, and the prices that people quote for the next large collider is very high. I would say probably these are worldwide things. We'll only build one. Almost all the countries in the world will contribute to it, as they do here. We have basically everybody paying some money towards this. And overall, as a fraction of the world's GDP, it's probably a reasonable thing. But I agree, we've got to make the case for it. I think that the no-lose was a special case, and I don't think we're going to find ourselves in that position. But I think we can make a strong argument that there's lots of exciting stuff that we can do. So I understand Sabine's comment. She's right that there is nothing that says it must be here. You will find something. But on the other hand, I think we have to go look, and we have to make the case for why it's useful.
Okay, anything else in the room? No? Okay, anything online?
Currently.
If not, okay, then it's a pleasure. Let's turn to the vote of thanks. A pleasure to introduce Professor Alexandre Zabi from LLR École Polytechnique. And maybe I can say, if you work on the level 1 trigger project as Alex has led, you have to be called Alex. So if I refer to the two Alexes, I'm going to try and say Alexandre and Alex, but they both go by Alex. But anyway, Professor Alexandre Zabi.
Thank you very much. Hello, everybody. I didn't know exactly what I was supposed to say. I thought it was a roast. So I watched a few of these shows on Netflix, and I realized it was not exactly what I was supposed to say. But so let me start right. Dear all, it's an honor to be here today to celebrate Alex's appointment as professor in this prestigious institution of Imperial College. It's nice to see so many of you here, really. Sorry, it's a bit maybe resonating here. Let me move a bit. Is it better? Yes, sounds better. Okay. It's nice to see so many of you here today, really. We had to clear our agenda to listen to Alex and this brilliant lecture. Thank you, Alex, for this. This institution is dear to me, because I started my young career as a researcher here as a postdoc in 2004, already 20 years. And I met Alex in 2006, only 2 years after I started. He was sent to CERN on LTA. So if you guys don't know what an LTA is, a long-term attachment or license to adventure in some ways, because we were sent to CERN, but it was a really exciting time. I mean, it was the time where we started to build the experiment, okay? And we got to see, sorry guys. we got to see the first ever collision recorded by the experiment. So this was a very, very important moment in the field, and resonated everywhere. Was the first line of every newspaper. So we shared an office with Alex, and we became good friends from the start, really. It was an intense period. We were working hard. We had to make it. It had to work. A lot of people that worked 20 years to design these machines, we had to put it together. But we found a way to enjoy ourselves. I mean, it was Geneva, so Geneva has much to offer. If you've never been there, I suggest you take a flight and have a fun there, because look, it's summer at the lake, it's winter at the mountains, and international crowd. So, and also working for Imperial, you have to learn about beer o'clock, as Matt used to call it. Okay. So Alex stroked me as a bon vivant, as we say in French. I guess you know what it means. You know, he appreciates fine food and very high quality beverages. So we were meant to become friends and understand each other, right? So, but since it's a vote of thanks, I need to thank you for something. So I want to say thank you, Alex, for being the most efficient TripAdvisor and Google all assembled at the same time, because he finds the best place to have dinner and the best place to drink. Just ask Alex, he will tell you where to go tonight. He knows everything, I can tell you. So we worked together on the trigger system. Really, this is where we learn our stripes. We were involved in the first phase of the data taking. We were both involved in the upgrade afterwards during the long shutdown in 2013. So we were in the trenches, really, with a lot of familiar faces that I see smiling back at me, actually, in the crowd. So at that time, I was not Imperial anymore. I was LLR, so I was at École Polytechnique in Paris. But we continued to keep this strong collaboration together. And in fact, our teams work together even today. So our students work together, collaborate, right? Many of our students became postdocs at Imperial. We attended each other's, student defense. That was a good, excuse to drink also together. And recently, we also built a joint project, CNRS Imperial, which is ongoing at the moment. Alex can speak about physics, right? He understands many aspects of its experimental side, including physics, detector physics, electronic system, software. He's clearly passionate about it, as you have heard today, and he's made an impact in all the projects he's been involved with. So, and he was always very keen, and he is always very keen on motivating innovations to help us improve the understanding of matter. So in this line of research, we all have a hobby. We all have our pet project. I was more on the Higgs physics since my PhD, and I was really impressed with the fact that Alex was involved in so many different areas. I met him, he was still making plots for Zeus. He was involved in a large variety of physics, from deep inelastic scattering at Hera in Hamburg and to the supersymmetry at LHC. And for me, the scale goes where you understand about physics when you understand the jokes about B-physics. So, sorry, Rob, but really I found myself very often in these conversations with him and Oliver and our colleague Greg Landsberg making fun about physics and every distribution being flat, and you look at each other like, what the hell is he talking about? But I was really impressed with the fact that he is so curious about all of this that he could really understand even these sort of jokes. So Alex is modest, that we all know. He's discreet. He doesn't really fancy all of these, big displays, to be honest. Even told me he was dreading that event. But you see how great he did. And he prefers sharing good times with small group of people where he could speak about science and exchange about all of these great new ideas, He would even find any way to avoid any improvised large workshop dinners I was trying to set up, to be honest. But really, I heard him giving many talks at CMS, and he's always been brilliant at his exercise. And really, today, I wish I was one of his students getting the chance to listen to his lecture, because you guys are very lucky. Alex looked after the CMS Level 1 Trigger project as a project manager for 4 years. And he appointed me one of his coordinators, so we worked closely during that time. And he showed absolutely incredible leadership. I learned much from him, and in particular, the ability to balance complex dynamic of forces in a group of people. And he's very good at it. He's not only good at physics, but he can really manage these sort of projects and make them thrive. So it really motivated me to look after the project after him, which I did for the past 4 years as well. And he always made himself available whenever I needed advice and guidance. So, Alex, I really, truly, sincerely thank you for that. So, when it comes to this conclusion, you may ask me, okay, so Alex, it seems like you learned much more from him than he learned from you. I might say yes to that, but I did have a chance to teach him something, which is snowboarding. So I think I've been terrible at this because he never went back on a board ever since. Sorry, Alex. So I really thank him for being a great friend and a wonderful colleague and really a pleasant person to work with. And I would like everyone here to please join me in congratulating him on his appointment. Alex.
Thank you. Fantastic. 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 Thank you, Alexandre. Thank you, Alex, for the talk. And if I may say from my side, for everything you've done for our community, for the wider field. Thank you. Turning to the audience, thank you. It's great to see so many familiar, so many non-familiar faces. I hope there's something there, as I felt, for everybody. And so thank you. And can I just finish by inviting you to a drink outside? So please, let's carry on the conversation over a drink. But thank Professor Alex Tapper. Thank you.
Can you hear this? Can you hear that? Check, check, check. Mic check, mic check. Yeah. Okay. Check, check, check. Yeah, no. Yep. Testing, can you hear that? Can you hear me? Check, check, check. Test. Okay.